In this video, we will give another illustrative example of how a first-order equation can be used to model a physical system. So first-order equations, that's what we're looking at here, first-order ODE, and we're going to use them to model a physical system. You've already seen several examples involving different things. For example, we've seen population dynamics modeled by first-order ODEs, also continuous compound interest was used to model problems both involving loans and savings accounts, also mixing problems, water flowing in and out of tanks with various solutions inside, and some of you may also have seen a simple example of a motion of a projectile. In this video, we will actually revisit the last example, that is motion of an object, but we shall recast the resulting differential equation from one in which the independent variable is time to one in which it is distance. In so doing, we will use a simple change of variables and therefore also the chain rule. So there will be a change of variables, and as a consequence, we will have to use the chain rule. But before I do that, I want to include a word of attribution. The two examples that follow are actually based on material taken from the ODE book by Boyce and DePrima. Some of you may recognize that name, those names. They were the authors of the textbook that was used in this course before we actually went online. Okay, let's now consider the first example. It reads as follows. A body of constant mass m is projected away from the Earth in a direction perpendicular to the Earth's surface with an initial velocity v0. Assuming that there is no air resistance, but taking into account the variation of the Earth's gravitational field with distance, find an expression for the velocity during the ensuing motion. Also, find the initial velocity that is required to lift the body to a given maximum altitude, say A, above the surface of the Earth, and find the least initial velocity for which the body will not return to the Earth, that is, the escape velocity. Let's now translate that into mathematics. So here's the center of the Earth, and there's the surface of the Earth, and we'll assume the radius is r, and the projectile goes along a straight axis like this. Here's the body. And we're assuming no air resistance, so there will be exactly one force acting on it, namely the force of gravity. The distance from the surface of the Earth to the body is x. And we now apply Newton's law of gravitation, which tells us that F equals minus mg r squared divided by r plus x squared. Well, it doesn't tell us exactly that. What Newton's law does tell us is that the force is proportional, inversely proportional, to the square of the distance from the center of the Earth. So it looks like this, minus k over x plus r squared. And if you put x equals 0, that is at the surface, the force, of course, is just the weight, which is mg. And so it follows that k equals mg, and one gets this formula for the force on the object. Okay, let's invoke Newton again. It says that F equals ma, which is m dv dt. And so that will be equal to minus mg r squared over r plus x quantity squared. Looks like a first-order differential equation. The problem is we have an x on the right-hand side and v is differentiated with respect to t. So we have to make a change of variable and apply the chain rule. namely that dv dt is dv dx, dx dt. But dx dt, of course, is just v, so this is v dv dx. And so we now get the equation that m v dv dx is equal to minus mg r squared over quantity r plus x squared. A nice first order ordinary differential equation, which we note is separable. So this is separable. And so we can actually solve it. So let's separate the variables. If we do that, we get v dv dx. The m's cancel. Is minus g r squared over r plus x quantity squared. And then we integrate both sides. So let's integrate this with respect to x on the right. And the result is the following equation: v squared over 2 e squared over 2 is equal to gr squared over r plus x plus a constant of integration. To determine that, we use the fact that the initial velocity, v at 0, is v0. And if we then plug that in, we get that c is equal to v0 squared over 2 minus gr. And then plugging that into the equation for v squared over 2, multiplying by 2 here, and taking the square root, we get the following expression. So I need to proceed to the next screen. Continuing from the last screen, I've rewritten the equation that we had arrived at, and we can solve this equation rather easily for v. We just have to multiply by 2 and take the square root. And so we get v equals plus or minus the square root of the quantity v0 squared minus 2gr plus 2gr divided by r plus x. And of course, since the projectile is moving up, we have to take the plus sign. Okay, so the question next was, what's the maximum altitude? Maximum altitude will occur when the velocity decreases to 0. So if we set this equal to 0, we then get the equation, of course square, we get the equation v0 squared minus 2gr plus 2gr divided by r plus a equals 0. And then you have to solve for a little bit of algebra there, which I won't go through, but I'll tell you that the altitude is v0 squared r divided by 2gr minus v0 squared. Now to compute the escape velocity, we solve this last equation for v0. Again, a little bit of algebra. v0 turns out to be the square root of 2gr times the quantity a over r plus a. And now the escape velocity will be such that a, of course, does not take on a finite value. And the way you find it is you let a tend to infinity. And of course that quotient inside the radical will tend to 1. And so we get that the escape velocity, v sub e, is the square root of 2gr. That's the minimum initial velocity that one must impart to the rocket, if you will, to ensure that it escapes the Earth's atmosphere. Incidentally, that quantity is approximately 6.9 miles per second. So, I don't know, 36,000 feet per second. We can apply this technique actually in other motion problems, and so let's do that with a second example. Okay, the second example is the following. A rocket sled having an initial speed of 150 miles per hour is slowed by a channel of water. Assume that during the braking process, the acceleration A of v is given by the equation A of v equal minus mu v squared, where v is the velocity and mu is a constant. So it's slowed down at a rate proportional to the square of the velocity. If it requires a distance of 2,000 feet to slow the sled to 15 miles per hour, find the value of mu and find the time required to slow the sled to 15 miles per hour. Alright, so we have this sled moving along in a direction like this, and we're given that the acceleration as a function of velocity is minus mu v squared. And we're asked various questions. Before I do that, let's write down the initial velocity. We were given this 150 miles per hour, and mu is a constant, which we don't know. We write down F equals ma, which, as we saw earlier, was mv dv dx. And so it's also equal to m minus m mu v squared. By the hypothesis on the acceleration, the m's cancel, and we get a first order ordinary differential equation again, even simpler than the last time. Notice one of the v's cancels, and so we get the equation dv dx equals minus uv. That's easy to integrate, and we'll do that on the next page. So here's the equation that we were in the midst of solving. It's, again, pretty simple separable equation. And if you put the dx on its side, bring the v down here, integrate both sides, you get the equation very quickly that the log of v is equal to minus ux plus constant integration c, or same thing, v equals, let's say, k e to the minus mux. K is e to the c. So there's the solution, and now let's use the initial value. V of 0 is 150 miles per hour, and so k is 150. So now we have the equation v is 150 e to the minus mux. And next we were told that it takes 2,000 feet to slow it down to 15 miles an hour. So if we put x equal, not 2,000, remember, because it's in miles, so x is equal to 2,000 over 5280 feet per second, 5280 feet in a mile. And then plug that in, and you get the equation 15 equals 150 e to the minus mu times this value of x. And there's a little work there to solve. You get that mu is equal to 66 over 25 times the log of 10, which is approximately equal to 6. Then we're asked, what's the time required to do that? Well, that's obtained as follows. V, remember, is dx dt, and so that's equal to 150 e to the minus mux, where mu is this value up here. Another first order equation that we can separate and integrate, and so we can rewrite this as e to the mux dx equals 150 dt, and integrate both sides. On the left hand side we get 1 over mu e to the mux, and the right side we get 150 t plus c. And the last thing to do is determine C by using the fact that at time t equals 0, the sled hasn't gone anywhere, so x of 0 is 0. So you plug that in, which enables you to determine C, namely C is 1 over mu. And then you solve that equation for t, which I'll just write it down. T turns out to be 1 over mu e to the mu times, again, this value, minus 1, all divided by 150. Notice that t is measured in hours. It turns out to be a rather small number. In fact, it's approximately 35.5 seconds. Okay, so that solves the problem. And the last comment I'd like to make is that this method illustrates what in the text, in the notes, is called the IRS method for solving applications, word problems, if you will. The first I stands for identify the problem. So identify problem. R stands for reduce. Reduce to math, or reduce it to an equation. And S stands for solve. Solve the equation. Okay, so there's an outline of how we can use first-order equations to model physical problems, and then the solutions of those equations tell us the nature of the physical system that we're trying to understand.